Good afternoon, friends. First of all, I want to introduce myself Ankit Acharya, working as an assistant professor in Hasmukh Goswami College of Engineering in subject of mathematics. So today my topic is vector spaces. Vector space and contain of today's topic is vector space, then subspace, span of a set, and linearly independent of a set. Here is the first definition of a vector space. Let's see what is the definition. Let V denote an arbitrary set of objects called vectors. So the set V is called vector space if it satisfied the following 10 conditions, following 10 exams. Sometimes it is also called linear space, linear vector space or linear space. So here is the first condition. If UV belongs to vector space V, then U plus V is also belongs to V. That is the condition closure under addition, right? Second condition is U plus V is equal to V plus U. That is also true for all UV belongs to V. That is called commutative law. Third condition is associative law, which is U plus in bracket V plus W, that is equal to in bracket U plus V plus W. That is also true for all UVW belongs to V. It's called associative law. The fourth condition is for all U belongs to V, there exists theta. Theta means identity. So this condition is called existence of identity. So for all U belongs to V, there exists theta belongs to V such that U plus theta is equal to U. Right? So this condition is called existence of identity, and that is also true for all U belongs to V. Fifth one is for all U belongs to V, there exists minus U belongs to V such that U plus minus U is equal to theta. That is called existence of negativeness. So that is also true for all U belongs to V. Okay, so these 5 conditions are for additions, and next 5 conditions are for scalar multiplication. The first one is, that means overall the 6th condition is for any k is a scalar. If k is a scalar, so normally we are taking scalar as a real number, right? So if k is a scalar and U is any vector of V, then k into U, that means scalar multiplication of k into U is belongs to V. It's called closure under scalar multiplication. The 7th condition is k into U plus V is equal to k into U plus k into V for any scalar k and for all UV belongs to V. That is called distributive law for addition in vector space V. The next condition is k plus m into U is equal to k into U plus m into U, where k and m is any scalar and U belongs to vector space V. That is called distributive law of numbers. The next condition is in bracket k into m into U, that is equal to k in bracket m into U, that is equal to m in bracket k into U. That is also true for any m k is a scalar and U belongs to V. So it's called associative law. And the last condition is 1 into U is equal to U. That should be true for all U belongs to V, identity for multiplication. Okay, so we again see this definition of vector space. This first 5 conditions are for addition. First one is closure under addition, second one is commutative law, third one is associative law, fourth one is existence of identity, fifth one is existence of negativeness. So this first 5 conditions are for addition and the next 5 conditions are for scalar multiplication. The first one is closure under scalar multiplication, next is distributive law for addition in V, and then distributive law of numbers, then associative law in scalar multiplication, and then identity for multiplication. Okay, so if any set, any non-empty set satisfied this 10 condition, then we can say that a given set is a vector space. Okay, otherwise if any one condition from that 10 condition, if any one condition is dropped for any particular set, then we can say that the given set is not a vector space. Okay, so keep in mind that this 10 condition is very important to become a vector space. Let's see some example of vector spaces. Here is the first example. We have to prove that the set of all pairs of real numbers of the form 1x, that means the first coordinate is definitely 1 and the second coordinate is any real number, with the operation defined as 1x plus 1y is equal to 1x plus y, and k into 1x is equal to 1 comma kx is a vector space, that we have to prove. So under the given addition and the scalar multiplication, right? So what is our set? The set V is equal to, set theoretically we can write V is equal to, the first coordinate should be 1 and the second coordinate is any real number. So only those elements are in the set from R2 such that the first coordinate should be 1 and the second coordinate is any real number. Only those elements, only those vectors of R2 would be in V, set V, right? So how we define addition? 1x plus 1y is equal to 1x plus y, 1 comma x plus y, and the scalar multiplication defined as k into 1 comma x is equal to 1 comma k into x. So we use this addition and the scalar multiplication, okay, whatever the given in the statement. So let's try to prove one by one all the 10 condition, try to prove. Here is the first condition. For u plus v is equal to 1x plus 1y, that is equal to 1x plus y, right? That is already defined in the statement. That is also belongs to v. Okay, why this is belongs to v? Because you can see the first coordinate is 1 and the second coordinate x plus y, that is also real number, because x and y both are real numbers, so addition of any two real number is also real number. So that's why this element belongs to v, and this is true for all uv belongs to v. Okay, the second condition, u plus v is equal to 1 x plus y, that is equal to 1 y plus x, because x and y are real numbers. So in real number we know that x plus y is equal to y plus x. Okay, commutative law in real numbers is always true. We know that x and y are any real number, then x plus y is equal to y plus x. So we use that one. So 1 x plus y, that is equal to 1 y plus x, that is equal to 1 comma y plus 1 comma x. Okay, that we can write using the definition of addition in the statement, that is equal to v plus u. So you can see that we prove that u plus v is equal to v plus u, and that is also true for all uv belongs to set v. Okay, the second condition is also satisfied. Let's see the third condition, associative law for addition. In bracket u plus v plus w is equal to 1 comma x plus y plus 1 comma z. So now we use the definition of the addition which is given in the statement, that is 1. Now addition of that two vector can be written as 1 comma in bracket x plus y plus z. Now associative law in real numbers, that we have that in bracket x plus y outside the bracket plus z, that is equal to x plus in bracket y plus z, that we know for real numbers. So we use that one in the next step, that is 1 comma x plus in bracket y plus z. So that is equal to 1 x plus 1 y plus z, and that is equal to u plus in bracket v plus w, and this is also true for all u v w belongs to v. Okay, so first three conditions are satisfied very easily. Clear? Now next is identity for addition. Now for that we have to find such vector from the set such that u plus that vector, suppose that vector is equal to theta, then u plus theta is equal to u, and that is also true for all u belongs to v. So we have to find such theta. Let's see what is it. Take theta is equal to 1 0. Why it is 1 0? Because it satisfied this condition that if we take theta is equal to 1 0 belongs to v, set v, then u plus theta, that is u is 1x and theta is 1 0, so u 1x plus 1 0, that is equal to 1x, okay, 1x plus 0, so 1x, that is equal to u. Clear? So we prove that there is an identity theta is equal to 1 0 belongs to v. It satisfied this condition for all u belongs to v, that is u plus theta is equal to u, and similarly we can prove that theta plus u is equal to u, right? It's quite easy. And the next condition is minus u. Take minus u is equal to 1 minus x belongs to v, okay. So u plus minus u is equal to 1x plus 1 minus x. So 1 comma x minus x using the definition of addition which is given in the statement. So 1 x minus x, that is equal to 1 0, and that is equal to theta. So this is also true for all u belongs to v. We can find minus u, that is 1 minus x. If u is equal to 1x, then we take minus u is equal to 1 minus x, that is negative of u in addition. So u plus minus u is equal to theta, and similarly we can prove that minus u plus u is equal to theta. So first 5 conditions for addition is quite easily we prove, right? So let's see next 5 conditions. Next 5 conditions are for scalar multiplication. First condition is k into u, that is equal to k into 1 x, that is equal to 1 kx. Okay, we use the scalar multiplication which defined in the statement of example, right? So k into 1x, that is equal to 1 kx. That is also belongs to v, because see, first coordinate is 1 and the second coordinate is always real number, because k is real number and x is real number. So multiplication of two real number is also real number, okay. The next condition is k into u plus v, that is k into, we know that u plus v is equal to 1 comma x plus y, so we use that one, k into 1 comma x plus y. And now next is we use the definition of scalar multiplication which defined in the statement. So that is 1 comma k into x plus y. Now distributive law for real numbers that we have, that means we can write k into x plus y, that is equal to kx plus ky, right, quite easily, right? So we use that one in the next step, 1 comma kx plus ky, and that is equal to 1 kx plus 1 ky, okay. So k will be the outside from the bracket using the definition for the scalar multiplication, k into 1x plus k into 1y in the next step, and we know that 1 comma x is u and 1 comma y is v. So that is equal to k into u plus k into v. So we prove the 7th condition for the vector space k into u plus v, that is equal to k into u plus k into v, distributive law, okay. And that is also true for all uv belongs to vector space v, okay. Let's see the next condition. K plus m into u, that is equal to k plus m into 1x, that is equal to 1 comma k plus m into x. So 1 comma kx plus mx, because distributive law of numbers that we have in real numbers, so we use that one, k plus m into x is equal to kx plus mx. So that is equal to 1 comma kx plus mx, that is equal to 1 kx plus 1 mx, okay. We use the definition of addition which we use in the which is given in the statement of the example. So 1 kx plus 1 mx, and in next step we use the scalar multiplication, definition of scalar multiplication, okay, for the example, that is k into 1x plus m into 1x, that is equal to k into u plus m into u. That is also true for all km belongs to R and for all u belongs to v. The next condition, in bracket k into m outside the bracket u, that is equal to in bracket k m plus into 1x, that is equal to 1 in bracket k m into x, that is equal to 1 k in bracket mx, because this property we have for real numbers, so that we use that one. So 1 comma k into mx, k into 1 mx, that is equal to k into 1 mx, and that is equal to k into mu. So for this is also true for all k m belongs to R and for all u belongs to v. The next condition is last condition, identity for scalar multiplication. 1 into u is equal to 1 into 1x, so that 1 is multiplication with x, so 1 into x is x, so that is equal to 1x, and that is equal to u. So here we prove all the 10 condition for the given set under the addition and scalar multiplication, which is in the statement for the example, right? So you can see the all 10 condition we prove for the this set. Okay, one by one we prove all the 10 conditions. So that's why we can say that the given set is a vector space under the given addition and scalar multiplication, right? So V is a vector space under the given addition and scalar multiplication. Clear? Let's see one more example for vector space. This example is quite good. Let V be a set of positive real numbers with addition and scalar multiplication defined as x plus y is equal to x into y. So how we define addition? Addition of any two real number, that is equal to multiplication of that two real number, that is defined in the statement of the example, right? And c into x is equal to x raised to c, but c is any scalar, so c is a real number and x is also real number. So scalar multiplication we define c into x is equal to x raised to c. Show that V is a vector space under the given addition and vector addition and scalar multiplication. Okay, so first of all, what is our set V? V is any real number, positive real number.